So here I have a circuit that's set up in series. I have 3 light bulbs, and I'll talk about the rest of the circuit later, but as you can see, there's something is coming in here. This is connected to something, which goes through this bulb, through this wire, through that bulb, through that wire, through that bulb, and back out to this wire. So here's my ins and outs feeding my light bulbs are here and here. Now, what's coming in on this side is coming through my switch. So when I close my switch, that closes that loop. That follows, connects to my battery. If you follow, my batteries are connected in series to each other. And then I have this wire connected to my ammeter. This is actually a multimeter. It measures multiple things, but right now I have it wired and connected to measure current. So it's technically acting as an ammeter right now. It goes through my ammeter. That's how current measures. You have to make it go through the meter, then back into my circuit. So there's my closed path. Batteries, switch, light bulb 1, 2, 3, through my ammeter, back to my batteries, closed path. So I have a circuit set up here. Once I close the switch, light bulbs turn on and I'm getting a reading over here. Hopefully you can see, but I'm reading 0.20. This thing is, I have it, it's identical because this is also the same thing, but this I have it set up to measure voltage. Like I said, this is a multimeter, so this can measure a bunch of things: resistance, voltage, current, a bunch of things. So I have this set up to measure voltage. So if I were to get a battery, this is the standard 1.5 volt battery. If I were to get a battery and connect it, the 2 terminals to my 2 probes, I get a reading, and I'm getting 1.8. This is a 1.5 volt battery. I'm reading 1.8, and that's because what we have here is no load on this battery. There's nothing connected to this battery, so this is sort of more of an ideal scenario. Once I connect this to something and once current starts flowing, I'm going to start removing charge from one terminal as it starts being attracted and flowing to the other terminal. Once that starts happening, immediately the voltage difference between these terminals drops. Once that happens, the actual voltage difference between the terminals becomes more like 1.5. So just understand that when we actually have a battery without a load on it, when you measure that voltage, it's actually higher than it really is once you actually connect it to a system. So anyways, just so that you understand how this measures voltage and this measures current. This is similar to what you had, but the versions you had are analog. So there's a dial that moves up and down. These are digital. So they're measuring the same thing, but of course it's easier for me to set this up for the camera. So I'm using these in lieu of the other ones. So anyways, what I want to do is I want to make some measurements of current and voltage to determine the brightness of these. Okay? So right now, the current is 0.20. 0.20. I thought it changed. And of course, that's the current for all of these light bulbs, because the current that flows through the meter is the current that flows through this bulb, which is the current that flows through that bulb, which is the current that flows through that bulb. That's the thing about things connected in series. So 0.20 is the current through all these bulbs. Now these bulbs are pretty similar. They're not identical, but they're pretty similar. So that means that they have about the same amount of resistance. So when the charge comes out of the battery, it's going to lose some of its energy through this bulb. It's going to lose some more energy through this bulb, and then it's going to lose the last part of its energy through this final bulb. Because once it gets here, if we ignore what's going on in the meter, once it gets here, it's basically back at the battery. So all the energy that was built up on one terminal will be lost by the time it goes through all bulbs. So what I'm going to do now is I'm going to measure the voltage of this bulb over here, and we get about 1.5. The negative that you see here simply implies that I've switched my terminals. So if I were to flip these, I would make that negative disappear, right? So it's now about 1.5 positive. If I come over here and do it for this bulb, also about 1.5, not quite, but about. If I go to this bulb, It's finicky. It's finicky. It's reacting. It's getting weird. It's a connection issue. Let me see if I can figure out what the problem is. Okay, there you go. Yeah. Okay, so there it is, almost 1.5. Once again, the connections of these can be finicky, especially if they're not connected really well, which you may have found in your activities. So anyways, as you can see, the voltage of all these is about the same. So all of these have a voltage of about 1.5. And if I go from beginning to end, okay, so if I go from the very first one as it enters my light bulb to the very last one as it exits my light bulb, my voltage is 4.35. Okay, not quite 4.5, but almost. Now, if you actually notice quite carefully, the other ones weren't quite 1.5, right? They were about 1.45. And if you multiply 1.45 times 3, which is what, of course, you just add those together, you should get about that value, 4.35. So all that we're showing here is that the voltage of this plus the voltage of that plus the voltage of that is really the voltage of the entire set of light bulbs. Okay? Now, if you know the current through them, which we do, and once again the connections are kind of just finicky, let's try to stabilize them a bit. I don't know why they're getting kind of weird here. If the connection is solid, what we have is a current through all of them of 0.2 and a voltage through across all of them of about 1.5. Okay, more specifically, it was closer to 1.45, but once again, for our case of approximation. So now what I'm going to do is the way I have this wired is I can remove this and unclip this. Now what you'll notice is, of course, they all turn off because I've interrupted the flow to all of them. But I can connect it here, and when I do that, then the current will flow from my switch through this bulb, and remember, this is essentially the end of your path because this is connected through the ammeter. This is connected to your battery. So wherever I connect this, that means charge will then go back to your battery directly once it reaches here. So if I connect it here or here, it will not go through this last bulb over here. It'll go through this one, and then back to your battery, which means I'll only have these two bulbs connected in my set instead of all three bulbs. So I can connect it here or here, and I get the same result. Now I'll prove it to you by connecting it, and you can see, first of all, I have current that's a little higher, okay, 0.24. I can go ahead and connect it over here. Let me move that wire, and once again I have the same current, and these are just as bright. So it doesn't matter where I connect it, because all that really means is if I connect it here, then it goes through here, and then once it reaches here, it's going to go straight to your battery, because this is no longer a part of my path. If I connect it here, then it's going to first go through this blue wire and then to my battery once again bypassing this. I'm going to connect it here just so that you can read that a little bit more clearly so that this is not in the way. So now I have a current of 0.24. Once again, that's through these two light bulbs. This is out of the picture, and the current is the same through both. Now, what would I expect my voltage reading to be? I have not changed my battery. It's the same three batteries. That means that the electrons that are coming out of this terminal have the same amount of energy than they did before, whether I had 3 bulbs or now 2. So they have the same amount of energy per charge, same voltage, which means that when they go through this bulb and then through this bulb and they're done, they're going to lose a different amount of energy per bulb because now they only have to lose or share their energy across 2 bulbs instead of across 3 bulbs. Now, this is kind of weird because in a way we're kind of saying like as if the electrons know that there's 2 bulbs versus 3 bulbs, and of course that's not what we're saying, but it's simply that when the electrons reach here, they will run out of their energy, so by the time they reach here, they must finish their energy, and which means that they're going to share between that bulb and that bulb. So these, first of all, you'll notice they are brighter compared to before. Let me connect it here, okay? So that's the brightness there. They are brighter right there. Now I'm going to go ahead and measure voltage. and I have a voltage of about 2.2 almost, 2.16, almost 2.2, and 2.12, not quite 2.2, but almost 2.2. Once again, they're about the same, pretty close. More voltage now. So this bulb right here in the middle is getting 2.12 volts, where it used to be getting 1.45 volts. So now the electrons that go across this bulb are losing more energy per unit charge than they were before, and I have more of those electrons going through it. So not only do those electrons have more energy that they will lose going across this light bulb because of the resistance of the bulb, but I have more of them. And those two things combined, the added current and the added energy per unit charge, meaning the greater the potential, is going to give you a brighter bulb, a brighter light source. Now I'm going to not explain as much, but once again I'm going to now remove this and connect it here, and what I'm doing there is only connecting this bulb. These are now out of the picture. Once again I can connect it here or connect it here and get the same result, and hopefully you can explain why. So I'm going to go ahead and leave this over here. You'll notice now I have 0.34, I have more current. This of course is brighter than it was before, and if I go to the voltage of this single bulb, then I'm going to get 4.3. Okay? Now if you remember from before, the entire voltage setup was about 4.35 originally in the very, very, very beginning. It's now a little bit less, partially due to the fact that this has been running for a while, and literally I have a little bit less potential difference because the battery is working hard to try to keep that potential difference. So that's part of it. And also it has to do with differences in terms of the connections, less wires and all that, and it's going to have some impact on the measurements. But the point is that now the entire voltage that I was getting before when I had all of them set up, that entire voltage is now pretty much going to this light bulb, which means that the electrons that are leaving this battery are going to lose all of that energy per unit charge across this single light bulb, and then they're back at the battery because this cable is connected to the battery. So they're pretty much going to lose all of that energy, and as you can see, there's a lot more of them now. So between the added current and the greater potential, we're going to produce the brightest bulb in this case. I'm going to go back and connect this at the very beginning. They're in series. I'm back to my 0.20. And if I remove any of these bulbs because they are in series, what should happen? This is something talked about in the video, when one of the videos I talked about sort of things that were in parallel. And what happens is I twist it off and remove, and they all turn off. Current goes to 0, everything turns off because I've interrupted the path. And that happens anywhere. You might think, oh, this is the first bulb, so of course once I do that they all turn off. But if I take off the last bulb, then I still interrupt the path and they'll all turn off, because if I take off this bulb, then I stopped the path. So it's not that the electrons will go through this bulb, and then stop. No, I've stopped the path, no more flow of electrons. So any bulb I remove, the middle, or this last one, or the first one, will have the same effect, which is I interrupt the entire circuit flow. Of course, the switch does the same thing. I come to my switch, I open my switch, they all turn off, close my switch, they all turn on. So the switch can interrupt the flow, but any of these bulbs being removed interrupts the flow. Same thing if they actually burn out. When the bulbs burn out, then the filament that the current is going through, that's shining, that's lighting up, burns out and breaks, and therefore they will turn off. Which is of course what happens in older Christmas lights, where now they have a better way of connecting them. But before they were connected in series in a string, and if one burned out, the entire set in that string burned out because they were simply connected in series. So anyway, so this is a quick sort of overview of some of these things with resistors in series. And the next video, I will walk through a couple of things in less detail, because the idea is hopefully you can make sense of things once you've watched this video. But that really is going to be doing things with resistors in parallel. We're down to this parallel setup, and there's several ways to connect this, but let me unplug this. And once again, it's the same external setup. What I've changed is internal here with my wires to connect the light bulbs. This, of course, is feeding out to my battery through my ammeter, so this measures my current. And what I have is whatever's coming in right here out of my battery feeds in here, and you can see immediately that it splits up. Some of this stuff coming out of here will go through this bulb if allowed with other connections, but some also can go through this wire if allowed through other connections. And if you just sort of follow these paths here, what I have is current can come in here and then go through. Let me get this wire. Let me connect this here, for example. Okay. Current can go through here, through this bulb, and then to my battery. Because remember, this is essentially my battery right here on the other side, right? So my current can exit my wire here, feed in here, go through this bulb, out to my battery, and it's done. Current could also come out of this wire, go through this wire here, and then go through this bulb, through this wire back here to my battery, and it's back out. So my current could split here, go through this bulb instead, and then back out to my battery. Finally, current could go through this wire, and then through this other wire here, across this bulb, through this wire, and then this final wire, and then back out to my battery. So any current that comes out of here and splits up and goes through these other bulbs will go across that bulb, and then it's back out. Keep in mind that all these wires are conductive, which means that if I connect this here, it's the same as if I connect it here, because all of these are connected by wires, which means these are all essentially connected as one thing. So I can connect this here, or here, or here, and the effect will be the same. I could also connect this here, here, or here, and the effect will be the same, because these are all connected by wire, so these are all connected together as one thing. Which means I can connect this here, and then, and this here, and this will work, or I can connect this here and here, I connect this here and here, I can connect these anywhere. As long as I connect this on this side and this on this side, then current will do what I explained in some fashion. Now I'm going to turn the switch, and you'll notice that this is on, but these are not, and that's because I've unscrewed these off of their base. If I screw them on their base, then they turn on, which of course was a different outcome than when they were in series. Because if I take this off, there still is a path for these others because of how things are connected. If I screw this light bulb off, there's still a path for those. So unlike series, I haven't interrupted the flow by removing one of those light bulbs, which is how newer Christmas light strips are wired in this fashion, so that one bulb burns out, but the others, of course, still work. Okay, so let me go ahead and remove these. Let's go ahead and read the current reading. Notice the current reading right now is 0.33 amps, and that's when the when the electricity goes through this bulb only and then back out. These, of course, the electricity is not really going through those. The charge, the electrons are not going through those because they're not connected. So right now I have current of 0.34, and I have a voltage, if I just go ahead and measure this, of 0.41. Okay. Now if I put this one on, you notice firstly my current goes up 0.65, almost double, not quite, but almost double. And if I measure the voltage of this one, now notice it used to be 4.15 or something like that. Now it's a little bit less. And that's because I am making this work a little harder because notice I'm drawing more current. So I am making more electrons come out of this battery than I was before. So I'm making the batteries work harder to keep that potential difference. And of course it can't really keep up. So before it was able to keep a potential difference of 0.415. Now because I'm drawing more current, it's having a harder time to keep up that potential difference. So now I'm seeing a potential difference that's a little lower, okay, 0.37 almost. And if I come over here and measure that, that should be about the same, okay? Now the reason it's not identical is once again because of the wires, because of the fact that these bulbs are not identical. So I'm not going to get the same exact, but I should be pretty close, okay? 3.55 compared to about 3.7. Okay, so once again, close but not identical. Current has gone up with the 2 bulbs, and I would expect them with the 3 bulbs. My current to go up even more. It's now about 0.9 amps. So I'm making these work even harder than they used to, which means it's going to be even harder for the chemistry within the batteries to keep that potential difference. So I would actually expect my potential to go down even more than it was before. Now it's about 3.4. It was about 3.7, I believe, before for this one. This one is about 3.1. Once again, the reason why they're not identical is because of the wires, which of course have some resistance. They don't have negligible resistance. And if I go to this last one, that's even less because that's even more wires that they're having to go through, right? So I'm getting about closer to 3 right there.